Recording started.
This is a reminder, Class Connect sessions are recorded and distributed for learning purposes that are listed here. As always, please be respectful, appropriate, and participate, but please do not share personal information during the class session. Okay, so we should have our ticket open. I'm still waiting on green checks from about half of you, letting me know that you have entered the password and opened it up. So Adrian, Alyssa, Andres, Ariana, Brianna, Ciara, Demetrius, Libby, Grant, Haley. All right, go ahead, give me those green checks. Let's go, let's go. Awesome, you guys are on it. Okay, so we only have one day left of the quarter. Remember, school does end on Monday, right, for this quarter. So today we have our very last assignment, which is just part 2 of the final exam. It's only 3 questions. They're a little bit tougher, each question, just because they are a short answer question, so you do need to complete the sentences. And you'll basically, as you complete all the sentence starters, you'll basically write a small paragraph, okay? But again, I do have sentence starters there for you, so it's super easy. You just watch the video, you fill in the sentence starters with the information that you see in the video. Give me a smiley face if that makes sense. Smiley face if that makes sense. It's really, really easy, guys. I try to make it as easy as possible as we review this material. Cool, guys. So, one day left of the quarter. Smiley faces if that makes you happy. Thumbs down if you're like, oh my gosh, I'm not ready. Perfect. Okay, guys. So yes, school does end on Monday, the 29th at 11:59 p.m., which means 1 minute before midnight. So classes end 1 minute before midnight. You won't be able to access any material. No, Ty, so Monday we do have classes. So all you need to do on Monday, though, it's going to be super easy. You're going to come to class. You're going to check in with me. I'm going to double check that your grade is passing. And if it's passing, I'll give you the word for the day, and then you'll be able to leave. I'll give you your attendance for today, and then you'll be able to leave. Okay? But we don't have any more assignments on Monday. Yeah, so it'll be like a 5-minute check-in, and then you'll be able to go. Because I don't want to waste your time when you have probably other things that you need to be doing on Monday, right? Tuesday and Wednesday, you have both of these days off, so the 30th and the 31st. For those of you that celebrate Halloween, you will be able to have Halloween off, which is nice. And then Thursday, you'll see here November 1st will be our first day back for quarter number 2, and you will have 3 new classes. Thumbs up if you understand that. Looking at this calendar, again, Monday's the last day, 1 minute before midnight. Tuesday, Wednesday, you have off. And then we start the next quarter on Thursday. Yeah. All right. So I do want to give you a hint, though, guys, that I know the classes end at 11:59 p.m., but please do not wait to submit anything until 11:59 p.m. Here's the problem. You want to make sure you get your work done at least before 11 p.m. because at 11 p.m., that last kind of horrific hour of the quarter, everybody is online and everybody is trying to submit things. So this is the biggest time in which the system crashes. And if the system crashes, I just unfortunately won't be able to accept late work, even if you tell me it's a tech issue, because I'm warning you now that the system may crash, so you have advance warning, and because I can't confirm that you actually had tech issues. Give me a smiley face if that makes sense, okay? Yeah, you can absolutely work over the weekend. You can always work on the weekends. Yeah, so work on the weekend, get everything done on the weekend. That way you can have a chill Monday, or use Monday to get more stuff done if you need to. But just don't wait until after 11 p.m. on Monday to start turning things in. Because again, if the system crashes, I'm sorry, I have to be the bad guy, but I just can't accept late work. Okay? And plus, you've had an entire quarter to catch up. So we got to make sure we're on top of our work, guys. Okay? I try to be as nice as possible, but this is just the last hour. I'm usually like freaking out. I want to be asleep, so I just can't handle that at 11 p.m. Cool? All right. So here's what's happening today. So Andres, it starts again on Thursday, November 1st. So you can see these 4 days, right? So this is the last day. These 2 days you have off, and then coming back November 1st on Thursday. So a week from yesterday will be the first day of our second quarter. Cool. So today is super easy, guys. We're working on final exam part 2. Again, it's only 3 questions, but remember the final exam is the largest part of your grade. So between the short answers and the multiple choice that we did yesterday, this counts as 10% of your entire grade. So that means it's really important to get it done, all right? Each part counts as 5%. So again, the short answer, you had more questions, but they were easier. So even though today you only have 3 questions, it still counts as 5% of your grade because they're harder questions. So it's really important to do just as well today as you did yesterday. Give me a thumbs up if you understand. We got to make sure we do just as well on today's exam as we did on yesterday's. Awesome. So here you will see in a moment, I will be providing a video that goes over the answers for all 3 questions. What you will do is you're going to watch the video during class. You're going to work on the exam during class. If you finish it early, awesome. You can hang out until the end of class and just chill, maybe do something else, grab a snack while you wait. If you don't finish in class, that's fine. You can just keep on using that video and finish it on your own time after class is over. Okay, smiley faces if you understand. I know I'm asking for a lot of smiley faces right now, but I'm giving you a lot of really important information and I need to make sure you're on top of it. Perfect. Okay, that being said, I'll remind you of this, but I will be giving you the final word during the last 5 minutes of class. So I'm going to set a timer, and the timer will go off for you guys at 12:40. And at 12:40, I'll bring you all back in from the video. We'll go over any last announcements, and then I'll give you the final word, or the last word, which is the only question in your attendance ticket for today. Please don't ask me for it before then, because I'm going to be like, you should be working on your exam. Don't bother me about the attendance ticket, because I told you we're going to do that at the end of class. Okay? All right, guys, so today our 3 questions are going over waves, reflection, refraction, and conservation of energy. So we should be able to explain similarities and differences between longitudinal and transverse waves. We should understand how reflection is different from refraction, right? Reflection means light's bouncing off. Refraction means light is bending. They're 2 different things. And we will be reviewing the conservation of energy, the law of the conservation of energy, and providing some examples of how energy is conserved even though it's changing or converting from one type to the other. Give me a smiley face if you guys remember these, you feel like you're pretty confident in these topics. Yeah, we went over them. They were each their own units, so they should be pretty familiar. Awesome, guys. Okay, so here's what's going to happen. I have the video for you. I'm going to give it to you in a moment. Again, the video goes over the answers for all 3 questions. Watch the video, and you're going to continue working until the end of class. Again, if you finish early, sorry. I'm not going to give you the word then. You're just going to have to wait until the end of class. So you can sit there, do something else, chill, okay? So I will be giving that final word again during the last 5 minutes of class. Don't ask me for it before then because I'm going to be like, you need to be working on your exam right now. So here we go. I am going to paste the recording into the chat box, and I am also going to put it up on the whiteboard. Are there any questions? Green checks if we understand, red X's if we have any questions, we're confused about anything. Again, it's super easy, guys. It's I think it's like a 25-minute recording, and it's even shorter than yesterday's exam. So you guys will do awesome on it. You just got to work hard. I do want to remind you guys that for this exam, for this video I'm giving you, it does tell you on every slide, don't copy anything word for word. So you can use the information, but you just need to kind of put it in your own words. Smiley faces if you understand. So everything in that recording is free game. You should use the recording. Don't use anything from outside on the internet, because the internet is going to give you either incorrect information or information that's above your current learning level, which means that I will know that that you're cheating, right? It's being plagiarized, okay? So use what's in the video. Just make sure you don't copy it word for word. Put it in your own words, even if it's the same information. Cool, guys. All right, so I'm going to go ahead. I'm going to get this into your screen, and here we go. Okay, I'm going to try that again. 1 second, guys. Here we go. Let's go ahead and talk a little bit about waves. So, mechanical waves, remember that we talked about this in class. Mechanical waves do require a medium, meaning they require a solid, a liquid, or a gas in order to move. So think about the fact that sound is a mechanical wave, and if you ask yourself, can sound move through it? Then that means that it is that thing is a medium. So sound can move through a solid. Think about a piece of wood that you knock on. Sound can move through water, a liquid. Think about when you're underwater in the pool and you yell, someone can hear you. And sound can move through gas, like the air that's all around me. So those are all mediums, and those are all things that mechanical waves can travel through. Okay? Now, there are three types of mechanical waves we talked about in class. Today, for your question, we're going to go over longitudinal and transverse. So remember that longitudinal means that the particles are moving horizontally or parallel to the energy. So if our wave is going from one side to the other side, the particles are moving in that same way, left to right, left to right, left to right, and kind of vibrating in those spots. A transverse wave, on the other hand, those particles are moving perpendicular. So remember, if our wave is moving to the right, for example, this time the particles, though, are going up and down. Okay, they're moving perpendicularly or vertically. All right, smiley faces if that makes sense. Longitudinal, transverse. Okay, those are just really quick definitions. We're going to go over the actual definitions in a moment. Okay, so what I want you to do though, it is important to know that a similarity between longitudinal and transverse waves is that they are mechanical waves. So this is an important similarity that you can use in your question. So go ahead, take a moment, either write that down or take a snapshot, and then give me a green check when you've got it and you're ready to go. Okay, green checks when you're ready to go. We'll go ahead and give you actually like 40 seconds on this one. It shouldn't take too long. Hey Brennan, welcome to class. Go ahead and open up the exam. And then I'm waiting on green checks from Anthony, Bradley. Oh, thank you. Just waiting on Michelle and Savannah. Thank you, Michelle. Savannah, just waiting on you. Green checks. Oh, okay, no worries, Brennan. Make sure you grab a picture of this really fast if you haven't, though. Savannah, make sure we get a green check from you. Otherwise, we'll go ahead and move you to that MIA room. All right, so here's our actual definition. So definition of our longitudinal wave, it's when particle motion, so the motion of the individual little particles, is parallel to the direction of the energy, right? So if our wave is moving to the right, those tiny little particles are moving back and forth like this, moving back and forth left to right. Okay, so some examples of these are sound waves, right? We can see an example right here of sound waves where those little particles, these red particles, are moving back and forth. Okay, so really important, they're vibrating. Oops, that's a terrible color. Mustard yellow. So they're vibrating left, right, left, right, left, right, and the sound is going to our ear to the right. So smiley faces, if that makes sense, how these are parallel. Okay, so those little particles are moving left, right in their little spot, and those particles are parallel. We can see those lines right here are parallel. Okay. So again, this happens in sound waves as they push air towards your ear, and this happens in springs. If you push a spring, the little pieces of the spring are moving horizontally or parallel to the energy. So these particles move back and forth, but remember, they don't ever actually leave their space. So it's just like the stadium wave. Just because you're participating in the wave, you aren't actually leaving your seat. Okay, thumbs up if that makes sense. Okay, just because you're in the stadium wave doesn't mean you ever actually leave your seat. You're just moving around in your seat. Okay, that's the same thing with waves. Okay, go ahead and give me a green check when you have written some short notes to yourself or you have taken a picture of this. Again, we'll go ahead and give you 40 seconds, but we need you to work quickly, please. Go, go, go. All right, waiting on a green check from Anthony, Bradley, thank you, Brennan, Michael V, and Savannah. Make sure we get a green check from you, please. All right, let's keep going. All right, so the definition of our transverse wave, on the other hand, is that particle motion is going to be perpendicular to the energy, right? So if our wave is moving to the right, this time the particles are actually going up and down. And what this ends up doing is it creates that classic wave motion of this up and down wave. So for example, this happens in a guitar string. So if you pluck a guitar string actually has this up and down motion. And the particles in that string are moving up and down, but remember again, just like a stadium wave, they don't ever leave their space. They don't ever leave their seats. It's just that the energy is traveling throughout the string. So we can see this right here, where each part of that little string is going up and down, And if our energy is going to the right and these little particles are going up and down, smiley faces if you can see how these two lines are perpendicular to each other. Smiley faces if you can see how those two lines are perpendicular to each other. Okay, they're not parallel, they're perpendicular. It's a big, really important word when we're talking about our definition here. Okay, go ahead, take 40 seconds, make sure you have this information down for your question number 1 and give me a green check when you have this ready. Green check when you have this ready. You've either taken a picture or you've written stuff down. All right, waiting on Bradley and Brandon, Daniel, Helena, Jeremy, and Savannah. Oh yes, Actus, you know what that is? That's awesome. Yeah, that's how she was sitting in my lap without me holding her. Okay, Helena, no worries. Just take a picture of this. That way you have it for when you do open your exam. Okay, so let me know once you get that, okay? All right, guys. So just a reminder, looking at our exam. Oh, cool. That's awesome, Actus. For number 1, it is asking you about the definition of a longitudinal wave, right, which we went over here. It asks for an example, which we have some examples right here. It asks for the definition of a transverse wave, which we went over right here, and an example of a transverse wave, which we've put right here. And we talked about how they're similar, right? They're both mechanical waves, they both require a medium, and then how they're different, obviously, is going to be how those particles are moving. Okay, so that should help you do number 1. Okay, go ahead and give me a smiley face if you feel comfortable with answering number 1 on your own. Now that you have all that information, if you feel like you'll be able to put it in your own words and you'll be able to write complete sentences. Okay, perfect. Good to know. All right, guys, so our next topic for question number 2 is going to be about reflection and refraction. So remember that we talked about reflection. We talked about 3 things, right? Transmission, absorption, and reflection. And reflection specifically is when light reflects off of an object's surface. So it bounces off of an object's surface, right? So we can put right here, bounces off of a surface. Okay, and we saw this example right here where the light rays are coming in and then they bounce off of that surface. Now, this is really important to think about, right? Because remember that whatever light bounces off, that's the color that you actually see. Okay, so for example, in this case, you can see that all of the light rays bounce off, and therefore, what color is the object? Take a look at the object. What color is that object? If we end up seeing every single color light ray, what color does the object become? Yeah, right, it becomes white, because remember that every single light put together becomes the color white. We see it as the color white. Okay, so smiley faces, that makes sense. Reflection means we're bouncing off, and that tells us what color we end up seeing of our object. Perfect. All right, go ahead and answer question, take a picture of this or type some quick notes to yourself. Give me a green check when you have that. You guys have 40 seconds. All right, perfect. Let's go ahead, get green checks from Anissa, Anthony, Brennan, Daniel, Helena, Madison, Michelle, Rosemary, Samantha, Savannah. Yeah, again, guys, I know we're going through this pretty quickly, but if we don't go through it quickly, we won't get to every question. So just make sure you're taking lots of pictures or that you're writing yourself lots of notes so that you have the information to finish up once we leave class, okay? Perfect. All right, guys. So the law of reflection. So this is important. You need to understand that when things are reflecting, the law of reflection says that the angle at which that light comes off is always going to be equal to the angle at which it hit the surface. Okay, so this is what we call the angle of reflection being equal to the angle of incidence. So we can see this right here. If our flashlight comes into a surface at a certain angle, let's say 30 degrees, it's going to also bounce off at 30 degrees as well. Okay, smiley faces if that makes sense. Okay. All right, so let me go ahead and show this to you guys in a demo so that you can see how this works. All right, so let me go ahead and open up our content here. I'm going to share this with you. All right, smiley faces here if you can see my screen. Yeah, if you ever play with flashlights in a mirror, it's really easy to see this. It's pretty cool to see. All right, so under our additional reading materials, I'm going to go ahead and actually, sorry, no, it's underneath light. And go underneath light. I'm going to look at 8.03. Ow. And looking at 8.03, we're going to go over to page number 5 and click on this link right here. Okay, so what you're going to see is as our flashlight moves on the left side, the right side is going to reflect the same exact angle. Okay, smiley faces if you understand what you're looking for. Okay, so there's a mirror down here. We're going to look at how the light moves. And again, you can see this if you ever play with a flashlight in a mirror in your own life, okay? All right, so you can see the hand moving that flashlight, and you can see the angle changes exactly the same. Okay, was that too fast, or were you guys able to see that? Tell me in the chat box, was that too fast, or were you able to see it? Okay, perfect. Yeah, good, 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 good. All right, awesome. So let's go back to our question here. All right, guys, so go ahead and answer, take a picture of this or write some quick notes to yourself. We'll go ahead and give you a minute to work on that. Give me a green check when you have that information. Okay, green check when you have this. Go, go, go. All right, waiting on a green check from Anthony and Brennan. Helena, if you got a picture of it, let me know. Madison and Michael. Michelle and Rosemary. Green checks, guys, if you were able to get a picture / write some notes to yourself. Either of those is fine, just so that you have the information for later. Perfect, green checks from everyone. Okay, so now refraction is a little bit different. So it's going to ask for the definition of refraction, and what refraction is how light bends once it enters a substance. Okay, and the reason that this happens is because when light enters a substance, remember that it slows down. So for example, light travels slower in water than in air. So as it goes into water, it actually bends. Water actually bends the light wave. And we saw this when we put a pencil in a clear cup of water. So smiley faces, if you guys remember this demo or have ever done this yourself, when you put something into a cup of water, you'll notice that that pencil suddenly looks different underwater, right? In some cases, it even looks like it's completely broken off from the top part. Okay, and again, that's because of how light bends differently in water. So we can see here that light bends, these red arrows, you can see how light bends in one direction underwater, but once it gets to the air, it bends at a different direction. And so the result is you end up seeing a bent kind of picture under the water. Okay, go ahead and take notes on this one or take a picture. Give me a green check when you have that. You've got 1 minute. All right, waiting on green checks from Anthony, Brandon, Brennan, Madison. All right, got everyone. Perfect. All right, looking good. All right, Miss P, you're up.
All right, thank you. All right, guys, so we're going to be talking about the conservation of energy, and this is going to be helping you answer question number 3. And so if you look at question number 3, it's going to be asking you to give 4 examples of how energy can be converted. So you'll need to just be paying attention to each of the slides that goes over these examples, okay? And just like we've been doing, you'll just take notes or take a screenshot as we go through each one. Okay, thumbs up if this makes sense to you guys. Yeah, there are going to be several examples, and then we're going to go through each one. Yep, and you can always think of them on your own. Perfect, thank you. Okay, so recall that the conservation of energy is just that energy is neither created nor destroyed. Okay, instead, it's changed from one form of energy to another. So if you cannot create or destroy energy, right, so if you see energy changing from something, one kind to another, remember, it's not disappearing, it's just changing. It's being transferred, okay? Smiley faces, this makes sense. And we've talked about this. Okay, perfect. Okay, so for example, if you were to see a saw like this cutting a metal pipe, okay, you're going to hear a horrible sound, but then you're also going to see sparks flying all over the place. You're going to see light. And so what you're observing is you've got this electrical energy that is being used to power that saw. And of course, you've got mechanical energy too, because the little wheel is spinning around, right? But then what's going to happen is as it's cutting and all of this is being released, you're going to have this transfer of energy to light, because light energy is energy. And then the spinning saw blade, that's mechanical, it's moving around. And then you'll have these flying sparks, and this is heat. Okay, thumbs up if this makes sense to you. Again, so you've got the conservation of energy. You've got just a transfer of energy from, in this case, electrical to mechanical to light and to heat. Okay, so if you would please go ahead and take a screenshot or take your notes, and you guys have 40 seconds to do this. Okay? All right, guys, so just need your green check marks to let me know that you have saved your the screen, you have written down your notes. Waiting on green checks for Anthony and Alondra and Brandon and Brennan and Michelle and Savannah. Oh yeah, no worries, Alondra. It's okay. If you ever get kicked out, it happens. It happens to all of us. So you can always just come back in, and we can stick around after class to help you with anything that you missed. Anthony, just waiting on your check mark, as well as Michelle's and Savannah's. So we'll go ahead and put you in the MIA room. You can do that. So here are some examples. So when we again, remember, I just want to remind you, please don't copy any information you see here. Word for word, you're going to be using your own word to complete sentences. Okay, so an example of these conversions is chemical to mechanical. So for example, if you have fuel, and it could be food, it could be jet fuel, it could be gasoline, whatever the case, fuel is just a chemical. And it's converted to mechanical energy. It can be used to move a rocket, it can be used to move your bodies, it can be used to move a car, whatever the case. And so what happens is when you have chemical bonds, or when you have any kind of a chemical, whether it's in any kind of a fuel, what happens is as those bonds break in those chemicals, then that energy is transferred, okay? And if you transfer it to mechanical energy, that allows if it's your body, then it can move your muscles. It can help you think. It can have, if it's a car or a rocket, it's going to cause some kind of an axle to turn. And so you've just got this conversion, again, chemical to mechanical. Okay, so that's one example. If you're looking at, and you're going to be learning all about this next quarter, you're going to learn by looking at this, you'll be able to understand what this depiction means, because we're going to get into some chemistry. And so what's happening in this case right here with, like, say, for example, if you eat an apple, inside of that apple you have molecules, and inside of the molecules you have atoms. And when they bond together, they can actually, in this case, if you look at this, this is sugar, okay? And so what happens is when that reacts with oxygen in your body, it actually causes these bonds to break, okay? Think of it as Legos being pulled apart and put together into something else. And that could be one way to think about the conversion of chemical bonds into energy, okay? Smile face if this makes sense to you. Okay, so again, we're thinking about the different examples of the conservation of energy. So one is, again, chemical to mechanical. Another example could be solar to electrical. So we know that the sun is the biggest producer of energy that we know of, right? And so the sun that comes down and it hits us, we call this solar energy, and it's the radiation that reaches the earth. And so if you look around town or on your house or anywhere and you see these things called solar panels, what these are doing is they're converting light waves from the sun into electricity. And so these are called solar cells. And so this is another example of the conservation of energy. Okay, in this case, solar energy to electrical energy. Okay, thumbs up if this makes sense to you guys. Okay, so you can actually just capture that light energy and you can just convert it into electricity. Excellent. All right, so go ahead and take a screenshot. You have 40 seconds to help you answer question, to help you write your answers for number. And then give me a green check mark once you've done that. All right, thanks guys. So just need check marks please from Michael, and Michael, Michelle, and Savannah. Let's see here, and Brandon. And Brandon, it looks like you're still having some mic issues. Again, you can always watch the recording if you need to. All righty. Mrs. Larkin, do you want to check in with those students? Okay, so some more examples of the conservation of energy, how energy is transferred. Let's think about mechanical to electrical. So how many of you guys have ever seen a dam before? You may have seen the Hoover Dam. I've never been there, but I've heard it's awesome. Anyone ever been there before? So if you have water stored up above, and due to its position, you've got it up high, and you have that available. What is that energy called again? Remind me. If you, what is the energy due to position called? Write in the chat box, please. What is that called? If you've got water up stored in a lake or reservoir up behind this, yeah, that's just potential energy, right? So because of that position, you can use gravity to help you turn that into mechanical energy, that potential energy into kinetic energy, which is then can be used to mechanical energy, which in turn can be transferred to electrical energy. So gravity, it pulls water downhill. Okay, so you've got this water stored up here in this reservoir, right? And as it pulls down, as gravity pulls it downhill here, it can go through these this equipment in here, and it could be like a turbine. And as it pulls through that, it's going to capture that mechanical energy, and it's going to be turning that. And that in turn can be converted into electrical energy to power our houses, to power industry, different types of equipment, and so forth. And this is very, very effective, and this is a great example of, again, mechanical to electrical energy, that transfer of energy. Okay, so this is another example. Okay, then we have nuclear energy, and you may notice that sometimes there are multiple steps. So in this case, if you want to use nuclear energy, first you need to change it into heat energy, and from that you'll change it into electrical energy. And let me explain. So if you ever see pictures, or you might even see one in your house, there's actually a nuclear power plant that's relatively close to my house, for any of you who live in San Diego County. So if you notice, a nuclear power plant is going to take basically energy released by atoms. Okay, it's called, so in this case, it's nuclear energy. And so what they do is they slam them into, or what they do is they split them apart, and then it releases a lot of heat. So if you were to take an atom and you split it up, you're going to get this huge amount of energy. This is supposed to be like a star, okay? Huge amount of energy. And then what they do with that is they're heating up these really, really hot cores, and then they dunk them into seawater or lots and lots of water, and then that's going to create heat energy. So what happens if you put something really, really, really hot into water? Write in the chat box, please. What happens? There you go. So if you're taking this really hot object and you're putting it into water, okay, so this is water, and you're going to get all this steam, right, that's being released. Well, that can actually turn generators, and then that's going to be transferred into electrical energy. So you can capture that steam, you can turn things around, and it's going to be creating that. It's going to be turning that into electrical energy. Smile face if this makes sense to you. Okay, so that's an example of another transfer of energy, conservation of energy, nuclear to heat to electrical. All right, so go ahead, and you have 40 seconds to answer this question. And then I would like for you to please give me a green check mark once you have taken a screenshot or taken notes from what you see.
All right, guys, give me a smiley face if that made sense, all that information in there, if that helps you answer those 3 questions. Again, I'm sorry I didn't specify in the video that each of those slides goes over a little bit of each question. So for every question, there's like 3 or 4 slides that help you answer all of the parts of the question. Okay? Haley, if you have a specific question, go ahead, let me know. All right, awesome. Are there any other questions, guys, about that? Again, you do want to make sure keep the recording. Okay, so I'm going to link the recording again. Make sure you keep the recording. That way you can finish it on your own time if you didn't finish it during class. Awesome, looking good. Okay, so here was our objective for today, right? So question number 1 went over longitudinal versus transverse waves. Question number 2 went over reflection and refraction. And question number 3 went over conservation of energy and the examples. Okay? All right, yeah, so Haley, just keep in mind, like, are you actually looking at the exam? Like, if you look at the answer box in the exam, it goes over, like, here's the definition of longitudinal, and then you should just type what the definition of a longitudinal is based on the information in that video. Okay, make sure you don't copy it word for word. All you do, though, is you just kind of put it in your own words, right? Does that make a little bit more sense? If you watch the entire video and you're still confused, go ahead and email me and I would be happy to help, okay? Or you can come to support session later today and I can definitely help you there as well. Cool, okay, perfect. Yeah, exactly. So you can use the examples that I tell you. You just need to be able to explain the examples, right? So yeah, you can absolutely use all those examples. You really should use all those examples. I don't want you like Googling on the internet and finding outside sources that may or may not be right. Okay, cool. One other thing, sorry, Demetrius, I do need to talk to you really quickly. So just don't log out until after I talk to you, okay? Does that sound good, Demetrius? Cool, perfect. Okay, guys, here is your, oh, sorry. So make sure you complete that exam. Here is your last word, and I will see you all later. Bye, everyone.
Recording stopped.